Quick lesson on vertical acceleration as an application of the second law of motion. To review the second law of motion, we have the relationship of the net force to the mass and acceleration of a system, where we add up forces as vectors in order to calculate the net force. And these are the external forces. And we note that this is easier in 1D than it is 2D, and I wanted to take a lesson to analyze vertical motion as opposed to horizontal, just to get used to it. I'm also going to remind you of following the 4-step force analysis strategy, and I'll do this as we solve the problem. First of all, we're going to draw a general situation if it's not provided. Then we're going to do the free body diagram and all the details of the free body diagram. Then apply Newton's second law. That's when we'll identify the knowns and unknown quantities and solve. The light fixture problem says a light fixture of mass m equals 1.5 kilograms, and I can write that down, m equals 1.5 kilograms, is hung by a rope from the ceiling of an elevator. Okay, and they give us the general sketch over here. Rope, tension T, so we have a tension in this rope here, and there's the mass and the elevator, and we can see that the mass is suspended in the middle of the elevator. So there's no supportive surface underneath that mass, it's just hanging by the rope. And that has implications for our free body diagram. We notice there's no supportive surface, so there won't be a normal force. So it says, draw the free body diagram for the light fixture, label all forces in your free body diagram. So let's draw the free body diagram. It has to be free and over to the side, so I'm going to put that over there and have m in here, mass. We already noted that there is a tension holding the mass upward, and also because there's a mass, we know there must be a weight force, mg. So I'm going to draw the weight force on here as well. There's W. We have only vertical forces, so I'm going to assign a coordinate system. It doesn't matter whether you make up positive or down positive, as long as you're consistent within it when you're setting up the Newton's second law equation. So I'm going to apply that coordinate system. I don't know about acceleration yet, but I can add that in there as I learn more about the problem. It says, what is the tension in the rope when the elevator is ascending at constant speed? Okay, and then it says descending at constant speed. So we have ascending and descending. So we'll need to remember to answer both parts of that question. So let's look at ascending first at a constant speed. Well, when I think about constant speed, I'm going to note that that implies the acceleration equals 0, right? Words mean things and concepts mean things for quantitative values. And so acceleration is 0 at constant speed. And that can be used in a Newton's second law equation when I get it set up. And I think I have enough now. Now that I know acceleration is 0, I have my forces and I can apply Newton's second law. The net forces in the y direction, not x, y direction equals ma y. Well, I just decided the acceleration is 0, so I can put that over here. What goes over on this side is all the forces in the free body diagram. Whatever forces are in the free body diagram in the y direction goes over on this side with the right signs. So when I look at it, I have tension pointing up, that gets a positive value, and then W is pointing down, that gets a negative value. So I have T minus W. And we're going to see in this situation, when we use algebra, the tension equals the weight. And we want to find the tension in the rope, so we know the weight is mg. So we can calculate tension as the mass, 1.5, times the value for gravity, 9.8 is fine there, and we get the tension to be 14.7 newtons. And I'm going to note that it says tension, it will be upward, but we found the value. And this is when it's ascending, when it's moving upward. And what I'm going to note is when we did this problem, at no point did we mark or notate which direction it was moving, whether the velocity was upward or whether the velocity was downward. The acceleration is the quantity that goes into the equation, regardless of the direction of the velocity. And this is for ascending and descending. This is true for which direction you're going, if your velocity is up or down. So I'll put or descending. And I can put a box around that value for part B. Part C asks, what is the tension in the rope when the elevator is slowing down by accelerating upward? Okay, so in this situation, if it's slowing down by accelerating upward, that means it was initially moving downward. And so the acceleration is upward. Okay, so when we do part C, I'm going to note that the acceleration is 2.6 meters per second squared up. And I have that in my diagram. And up is positive in this situation. So when I set up Newton's second law, the sum of forces in the y direction equals ma(y). The acceleration gets a positive value, so I can leave ma over here. Over on this side goes the forces on my free body diagram, which is still just the tension upward and the weight downward. This equation makes sense to me because the tension needs to pull upward in order to cause a net acceleration upward, and it will be the larger force to cause a positive acceleration. It asks us to find the value for tension. I'll move weight over to the other side and note that weight is m times g, and I can simplify this equation by factoring an m out and put a plus g here. I can solve for tension by plugging in values, 1.5. The acceleration is 2.6, and I know the value of gravity is 9.8. When you run this through the calculator, you get a value of 18.6 newtons. I was just looking at the calculation in my head if it made sense. Okay, so that is for when it's slowing down by accelerating upward. The next part says speeding up by accelerating upward. Well, did it matter if this velocity vector was pointing downward or if it was pointing upward when I set up this equation? And again, the answer is no. Just like in this, the tension was the same for both up and down. Here, the tension is the same for both. As long as that acceleration is the same for both situations, regardless of the direction of the velocity, as long as the acceleration is the same value and direction, you will get the same for both. And that's an example of how to do this in a vertical direction. Again, whether you chose positive as up or positive as down, that might depend on the direction of your acceleration. And here it worked out that my acceleration was positive upward, so that worked out.